Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The intellectual ferment of 7th century Ujjain pulsed with the rhythm of celestial movements, a city where the heavens held sway over the minds of scholars. Ujjain, the astronomical capital of India, stood as a crucible of knowledge, a place where the legacy of Aryabhata, a towering figure of mathematical and astronomical brilliance, cast a long shadow. His work, meticulously documented in the Aryabhata, served as a foundational text, a cornerstone upon which subsequent generations of astronomers and mathematicians built their own theories and calculations. Yet, even the most revered works invite scrutiny, refinement, and sometimes outright challenge. The very nature of scientific progress demands it. The Siddhantas, the established astronomical doctrines, were not immune to this dynamic process. These complex systems, encapsulating centuries of observations and calculations, aim to predict the movements of celestial bodies and establish a framework for understanding the cosmos. They were comprehensive, but not infallible. Discrepancies existed. Observations sometimes clashed with predictions. The need for a more accurate, a more complete understanding of the heavens was a pressing intellectual concern, a challenge that drew ambitious minds to the task of refinement and correction. This was the landscape into which Brahmagupta emerged, a formidable intellect ready to engage with the existing frameworks and forge his own path. Brahmagupta's contribution was not a mere addition to the existing body of knowledge, but a significant re-evaluation and reorganization. He aimed to create Brahmasphutasiddhanta, a corrected doctrine, a more precise and comprehensive system built upon the foundations laid by his predecessors, but also critically examining and improving upon their shortcomings. This wasn't simply a matter of adding new data points. It was a profound undertaking, a systematic reassessment of fundamental assumptions and methodologies. The very act of creating Brahmasphutasiddhanta demanded a deep understanding of the existing siddhantas, a mastery of the mathematical tools used to model celestial phenomena, and a willingness to challenge established wisdom. The intellectual climate of Ujjain was one of intense engagement, a vibrant exchange of ideas that embraced both collaboration and competition. Scholars engaged in vigorous debates, rigorously testing each other's theories and calculations. The pursuit of astronomical accuracy was not a solitary endeavor. It was a collective pursuit, a shared intellectual quest that fostered both innovation and refinement. Brahmagupta's entry into this scholarly arena was not a quiet arrival. It was a bold declaration of intent, a signal that a new and powerful voice was joining the conversation. His approach, evident in the meticulous detail and intricate calculations presented in his monumental work, the Brahmasphutasiddhanta, exemplified both his mastery of existing mathematical techniques and his innovative spirit. He didn't shy away from challenging existing calculations or proposing novel approaches. His ambition was not limited to mere correction. It was to create a more complete and accurate understanding of the cosmos, a system that would serve as a beacon for future generations of astronomers and mathematicians. The scope of his undertaking, reflected in the sheer volume and complexity of the Brahmasphutasiddhanta, speaks to a commitment to intellectual rigor and a profound belief in the power of mathematical reasoning. The task Brahmagupta set for himself was immense. He inherited a complex system of astronomical knowledge, a tapestry woven from threads of observation, calculation, and philosophical interpretation. The challenge was not merely to improve upon this existing framework, but to demonstrate a clear and demonstrable improvement, to provide a superior model that would withstand the scrutiny of his peers. The intellectual stakes were high, the potential rewards immense. Success would elevate him to the ranks of the most respected scholars of his time. Failure would leave his work relegated to the dustbin of history. Ujjain, with its rich intellectual heritage and dynamic scholarly community, provided the perfect environment for such an ambitious undertaking. The city's reputation as the astronomical capital of India attracted scholars from across the land, creating a vibrant center of learning and intellectual exchange. This environment, characterized by intense debate and rigorous scrutiny, was precisely the kind of crucible needed to forge a work of lasting significance. Brahmagupta's entry into this intellectual arena was not a mere coincidence. It was a deliberate choice, a calculated move by a scholar, confident in his abilities and driven by a desire to contribute to the advancement of knowledge. The stage was set. The debate was about to begin. The intellectual legacy of Aryabhata was about to be challenged, refined, and expanded upon in ways that would reshape the mathematical and astronomical landscape for centuries to come. This was the context, the fertile ground from which Brahmagupta's genius would spring, a genius that would forever alter our understanding of numbers and the cosmos. Brahmagupta's arrival in Bilamala marked not only a geographical relocation, but also a pivotal moment in the history of mathematics. Within the intellectual hothouse of this astronomical capital, he turned his attention to a challenge that lay at the very foundation of arithmetic and algebra, the systematization of zero and negative numbers. This endeavor, audacious in its scope and profound in its implications, would forever alter our understanding of the numerical landscape. The concept of shunya, meaning void or empty, had existed in Indian mathematics for centuries, serving primarily as a placeholder in positional numeral systems. Its role was crucial in distinguishing, for instance, 100 from 1000, effectively marking the absence of tens in the former. However, despite its practical utility, shunyas lacked formal definition. It was a symbol without established operational properties. Similarly, negative numbers, while recognized in practical contexts such as debts or deficits, remained largely outside the realm of rigorous mathematical treatment. They were understood intuitively perhaps, but not integrated into a coherent algebraic framework. Brahmagupta recognized that a comprehensive system of arithmetic demanded a precise and consistent treatment of these elusive entities. Within the pages of his seminal work, the Brahmasphutasiddhanta, Brahmagupta embarked on a bold project of codification. He sought to define, explicitly and unambiguously, the algebraic rules governing operations involving zero and negative numbers. This was uncharted territory, a venture into the abstract realm of numerical concepts that had previously been left largely unexplored. His work represented a significant departure from earlier approaches, which had often treated zero and negative numbers as mere conveniences or practical tools, rather than as fundamental elements of a complete mathematical system. Brahmagupta meticulously laid out the rules for addition, subtraction, and multiplication involving positive numbers, negative numbers, and zero. He stated, for instance, that the sum of a positive number and a negative number is their difference, or that the sum of zero and a negative number is the negative number itself. These rules, seemingly self-evident to a modern student, represented a crucial step in formalizing the arithmetic of signed numbers. He codified the multiplication rules that govern the interaction of positive and negative quantities, declaring that a positive times a positive is positive, a negative times a negative is positive, and a positive times a negative is negative. These seemingly simple statements encapsulated a profound insight that the product of two negative numbers results in a positive quantity. a concept that often presents a stumbling block for students encountering algebra for the first time, even today. Brahmagupta's contribution extended beyond merely stating these rules. He provided a framework in which they could be consistently applied and understood. He was, in essence, creating a new language of numbers, one in which zero and negative numbers were not merely tolerated, but fully integrated into the grammatical structure of mathematical operations. This formalization was essential for the development of more advanced algebraic techniques. Without a clear understanding of how to manipulate zero and negative numbers, progress in areas such as solving equations and developing calculus would have been severely hampered. His most daring exploration, however, involved the treacherous terrain of division by zero. Here Brahmagupta ventured into the conceptual abyss of mathematics, grappling with a question that has challenged mathematicians for centuries. His attempt to define this operation, while not entirely in line with modern understanding, reveals a remarkable level of abstract thought. Brahmagupta proposed that 0 divided by 0 is 0. While this definition differs from the modern convention that division by 0 is undefined, it is important to understand the context in which he was working. He was attempting to create a consistent system of arithmetic, and his definition, though ultimately flawed, was a courageous attempt to extend the rules of arithmetic to their logical limits. It is important to note that Brahmagupta's understanding of division involving zero was nuanced and evolved over time. In some instances, he recognized that dividing a non-zero number by zero results in a quantity that is infinite or undefined. However, his struggle to reconcile these different perspectives highlights the inherent difficulty of dealing with the concept of infinity and the limitations of the mathematical tools available to him at the time. Despite these challenges, his willingness to confront this problem head-on demonstrates a remarkable intellectual curiosity and a commitment to pushing the boundaries of mathematical knowledge. Though his definition of 0 divided by 0 does not align with contemporary mathematical practices, its historical significance cannot be overstated. It represented an initial foray into a complex and subtle area of mathematics. It prompted further investigation and refinement by later mathematicians, both in India and elsewhere, ultimately leading to the more rigorous understanding of limits and infinity that we possess today. His bold attempt to grapple with the intricacies of division by zero serves as a powerful reminder that mathematical progress often involves exploring uncharted territories, even if those explorations lead to temporary dead ends or require subsequent correction. The rules governing the behavior of zero and negative numbers, as codified by Brahmagupta, form the bedrock of modern algebra and arithmetic. These seemingly simple rules, which every elementary school student now learns, represent a profound conceptual leap. The transformation of zero from a mere placeholder into a true number, capable of participating in mathematical operations, was an essential prerequisite for all subsequent mathematical developments. Without this conceptual breakthrough, the development of calculus, with its reliance on infinitesimals and limits, would have been inconceivable. Similarly, the rise of computer science, with its reliance on binary arithmetic and logical operations, owes a debt to Brahmagupta's formalization of zero. The implications of Brahmagupta's work extend far beyond the realm of pure mathematics. His contributions have had a profound impact on science, engineering, and technology. The ability to represent and manipulate negative quantities is essential for modeling a wide range of physical phenomena, from electrical circuits to financial transactions. The concept of zero as a number in its own right is fundamental to the development of coordinate systems, which are used to map and navigate the world around us. Brahmagupta's systematization of zero and negative numbers was not merely a technical achievement, it was a paradigm shift. It fundamentally altered the way mathematicians thought about numbers and their properties. It paved the way for the development of more abstract and powerful algebraic techniques. It provided the foundation upon which countless subsequent mathematical discoveries would be built. His work stands as a testament to the power of abstract thought and the enduring importance of rigorous mathematical foundations. The Brahmasphutasiddhanta served as a comprehensive guide to arithmetic, algebra, and geometry, demonstrating the interconnectedness of these mathematical disciplines. It included methods for solving quadratic equations, calculating areas and volumes of geometric figures, and determining trigonometric relationships. However, Brahmagupta's exploration extended into areas that presented even greater mathematical challenges. He turned his attention to the complexities of indeterminate equations, setting the stage for some of his most enduring contributions to number theory. The Brahmasphutasiddhanta served as a comprehensive guide to arithmetic, algebra, and geometry, demonstrating the interconnectedness of these mathematical disciplines. It included methods for solving quadratic equations, calculating areas and volumes of geometric figures, and determining trigonometric relationships. However, Brahmagupta's exploration extended into areas that presented even greater mathematical challenges. He turned his attention to the complexities of indeterminate equations, setting the stage for some of his most enduring contributions to number theory. Brahmagupta's investigations led him to grapple with equations that possess not a single definitive solution, but rather a spectrum of possibilities. These indeterminate equations, also known as Diophantine equations, demand solutions that are whole numbers, integers rather than fractions or irrational numbers. The pursuit of integer solutions introduced a layer of complexity, transforming algebraic manipulation into a quest for specific numerical relationships. Among these challenges, linear Diophantine equations, represented in the form x plus by equals k, and second-degree indeterminate equations, such as in x squared plus 1 equals y squared, later misattributed as Pell's equation, stood out as particularly formidable. These were not merely abstract mathematical puzzles. They held practical relevance in fields such as astronomical calculations, where precise integer values were essential for determining celestial positions and predicting astronomical events. To tackle these intricate problems, Brahmagupta devised the Kutakas method, a term that translates to pulverizer. This elegant algorithm provides a systematic approach to finding integer solutions for linear Diophantine equations. The core principle of the Kutakas method involves a process of successive division and reduction, akin to the Euclidean algorithm used for finding the greatest common divisor of two numbers. By repeatedly applying this process, the original equation is transformed into a series of simpler equations, ultimately leading to a solution in integers. Consider, for instance, the equation 5x plus 3y equals 7. The Kutakas method would proceed by first dividing the larger coefficient, 5, by the smaller coefficient, 3, resulting in a quotient of 1 and a remainder of 2. This yields the equation 5 equals 1 times 3 plus 2. Substituting this back into the original equation, we obtain 1 times 3 plus 2 times x plus 3y equals 7s. Rearranging the terms, we have 2x plus 3 times x plus y equals 7s. Now let x plus y equals z's, which gives us 2x plus 3z equals 7s. Repeating the process, we divide 3 by 2, obtaining a quotient of 1 and a remainder of 1, or 3 equals 1 times 2 plus 1s. Substituting this back into the equation, we get 2x plus 1 times 2 plus 1 times z equals 7s, which simplifies to 2 times x plus z equals 7s. Again, we introduce a new variable, x plus z equals 1s. At this point, we can easily find an integer solution, 1 equals 3s and z equals 1s. Working backward, we find x equals 1 equals z equals c minus x, which equals negative 1s. Thus, one solution to the original equation, 5x plus 3y equals 7s, is x equals 2, 5x plus 3y equals negative 1s. The brilliance of the Tuta-Taka method lies in its ability to systematically reduce complex equations into manageable forms, guaranteeing an integer solution if one exists. It represents a significant advancement in number theory, demonstrating Brahmagupta's profound understanding of the properties of integers and his ability to devise innovative algorithms for solving mathematical problems. Its modern counterpart is known as the extended Euclidean algorithm, a fundamental tool not only in pure number theory but also in applied fields such as cryptography. The RSA encryption algorithm, for example, relies heavily on the extended Euclidean algorithm for key generation and decryption, highlighting the enduring relevance of Brahmagupta's Tuta-Taka method in contemporary technology. The method is taught to students worldwide as a cornerstone of algorithmic thinking and number-theoretic problem-solving. Brahmagupta's ingenuity extends beyond linear Diophantine equations to the realm of second-degree indeterminate equations, specifically those of the form nx squared plus 1 equals y squared. These equations, mistakenly attributed to John Pell by Leonhard Euler, pose a considerably greater challenge than their linear counterparts. While Brahmagupta may not have found a general solution to this so-called Pell's equation for all values of n, he made a groundbreaking discovery that allowed him to generate an infinite number of solutions from a single known solution. This discovery is encapsulated in what is now known as Brahmagupta's identity. Brahmagupta's identity states that a squared minus nb squared times c squared minus nd squared equals a c plus nbd squared minus n times ad plus bc squared. This seemingly simple algebraic relationship holds profound implications for solving Pell's equation. If a and bc constitute a solution to the equation, a squared minus nb squared equals 1, and c and dt squared equals 1, then Brahmagupta's identity demonstrates that a c plus nbt and a d plus bct will also be a solution. In other words, if you have two pairs of numbers that satisfy the equation, you can combine them using Brahmagupta's identity to generate a new pair that also satisfies the equation. This process can be repeated indefinitely, yielding an infinite number of solutions. For instance, consider the equation x squared minus 6y squared equals 1. One solution is x equals 5 and y equals 2s, since 5 squared minus 6 times 2 squared equals 25 minus 24, which equals 1. Applying Brahmagupta's identity, we can generate another solution. Letting a equals 5, b equals 2s, c equals 5, and d equals 2s, we get a c plus nbd equals 5, times 5 plus 6, 2 times 2, which equals 49, and a d plus bc equals 5, times 2 plus 2 times 5, which equals 20. Thus, x equals 49 and y equals 20 becomes a new solution, and indeed 49 squared minus 6 times 20 squared equals 2,400, and 1 minus 2,400, which equals 1. This process can be iterated to find an infinite number of integer solutions to the equation. Brahmagupta's identity is not merely a clever algebraic trick. It reveals a deep underlying structure within the realm of quadratic forms. It demonstrates that solutions to Pell's equation are not isolated occurrences, but rather interconnected elements within an infinite family. This discovery represents a remarkable feat of algebraic ingenuity, one that would not be replicated in Europe for nearly 1,000 years. It showcases Brahmagupta's exceptional ability to recognize and exploit hidden relationships within mathematical structures. The significance of Brahmagupta's identity extends to modern algebraic number theory. It is closely related to the concept of the norm in quadratic fields, a fundamental tool for studying the properties of algebraic numbers. The norm of an element in a quadratic field is defined as the product of the element and its conjugate. In the context of Pell's equation, Brahmagupta's identity can be interpreted as a statement about the multiplicativity of the norm, demonstrating that the norm of a product of two elements is equal to the product of their norms. This connection highlights the profound and enduring impact of Brahmagupta's work on the development of modern mathematics. The Khuddaka method and Brahmagupta's identity stand as shining examples of his profound contributions to number theory. They demonstrate his mastery of algebraic manipulation, his ability to devise innovative algorithms, and his deep understanding of the properties of integers. These contributions not only solved specific mathematical problems of his time, but also laid the groundwork for future advancements in number theory and related fields. They are testaments to the power of mathematical innovation and the enduring legacy of Brahmagupta's intellectual prowess. Brahmagupta's mathematical ingenuity extended far beyond the realm of numbers. His profound insights into geometry and trigonometry provided powerful tools for measuring the world, both terrestrial and celestial. These contributions, characterized by their elegance and practicality, addressed tangible problems faced by mathematicians, surveyors, and astronomers of his time. He offered solutions that not only advanced theoretical understanding, but also had immediate applications in fields ranging from land measurement to astronomical prediction. One of the most celebrated geometrical achievements attributed to Brahmagupta is his formula for calculating the area of a cyclic quadrilateral, that is, a quadrilateral whose vertices all lie on a single circle. Before Brahmagupta determining the precise area of such a shape, especially when irregular, posed a significant challenge. While triangles were well understood, quadrilaterals presented a more complex problem. Brahmagupta's solution provides a remarkably concise and elegant answer. His formula states that the area of a cyclic quadrilateral with sides of length a, b, c, and d is given by the square root of the product of c's minus a's minus b's, n's minus d, where s is the semi-perimeter of the quadrilateral, calculated as half the sum of a b, c, and d. This formula, now known as Brahmagupta's formula, is a beautiful generalization of Heron's formula for the area of a triangle. Heron's formula, which gives the area of a triangle in terms of its side lengths, can be seen as a special case of Brahmagupta's formula, where one of the sides of the quadrilateral has length 0, effectively collapsing the quadrilateral into a triangle. The power of Brahmagupta's formula lies in its ability to directly calculate the area of any cyclic quadrilateral, regardless of its shape or irregularity, using only the lengths of its sides. This eliminated the need for complex geometric constructions or approximations, providing a straightforward and accurate method for determining area. It is a testament to Brahmagupta's ability to distill complex geometric relationships into a simple, usable form. In addition to the area formula, Brahmagupta also provided a formula for the lengths of the diagonals of a cyclic quadrilateral. If we let P and Q be the lengths of the diagonals, then Brahmagupta demonstrated that P is equal to the square root of the quotient of a times C plus B times D times a times D plus B times C divided by a times B plus C times D. and Q is equal to the square root of the quotient of A times B plus C times D times A times D plus B times C divided by A times C plus B times D. These formulas, while appearing somewhat intricate, provide a direct method for calculating the lengths of the diagonals given the side lengths of the cyclic quadrilateral. These formulas are a testament to his deep understanding of the geometric properties of cyclic quadrilaterals and his ability to derive elegant relationships between their different elements. Brahmagupta's work on cyclic quadrilaterals has had a lasting impact on the field of geometry. His formulas are still taught and used today in various applications, from surveying and architecture to computer graphics and geometric modeling. They stand as a cornerstone of Euclidean geometry, demonstrating the enduring power of classical geometric methods. Beyond his contributions to pure geometry, Brahmagupta also made significant advancements in the field of trigonometry, a branch of mathematics crucial for astronomy and navigation. Accurate trigonometric tables, particularly sine tables, were essential for predicting the positions of celestial bodies and calculating angles and distances. Brahmagupta sought to improve the accuracy and efficiency of these calculations. Aryabhata, a prominent Indian mathematician and astronomer who preceded Brahmagupta, had already developed methods for calculating sine values. However, Brahmagupta devised a second-order interpolation formula that allowed for more precise computations of sine values between those already tabulated. Interpolation is the process of estimating values between known data points. Brahmagupta's method involved using a quadratic function to approximate the sine curve, allowing for more accurate estimates than simpler linear interpolation methods. Specifically, Brahmagupta's interpolation formula can be expressed as follows. Let us assume we have a table of sine values at equally spaced intervals. To find the sine of an angle that falls between two tabulated values, we use the formula sine of theta plus h equals sine of theta plus h times the first difference plus h times h minus 1 divided by 2 times the second. Here, theta represents the nearest tabulated angle, h is the difference between the desired angle, and theta, the first difference, is the difference between the sine of theta plus the interval and the sine of theta, and the second difference is the difference between the first difference at theta plus the interval and the first difference at theta. This second-order interpolation formula represents a significant improvement over linear interpolation methods. Linear interpolation assumes that the function varies linearly between data points, which is often a poor approximation for trigonometric functions. Brahmagupta's quadratic interpolation method provides a closer approximation to the true sine curve, resulting in more accurate calculations. Brahmagupta's interpolation technique is a precursor to the more general Newton-Stirling interpolation formula, a powerful tool in numerical analysis. The Newton-Stirling formula allows for interpolation using higher-order polynomials, providing even greater accuracy. Brahmagupta's contribution can be seen as an early and important step towards the development of these sophisticated numerical methods. The significance of Brahmagupta's interpolation formula extends beyond its immediate application in trigonometry. It demonstrates a deep understanding of the concept of approximating functions using polynomials, a fundamental idea in calculus and numerical analysis. This idea forms the basis for many numerical methods used today in science and engineering, including methods for solving differential equations, approximating integrals, and modeling complex systems. Brahmagupta's work in geometry and trigonometry showcases his remarkable mathematical abilities and his commitment to solving practical problems. His formula for the area of cyclic quadrilaterals and his second-order interpolation formula for sine values are testaments to his ingenuity and his deep understanding of mathematical principles. These contributions not only advanced the state of knowledge in his time, but also laid the groundwork for future advancements in mathematics and related fields. They are enduring examples of the power of mathematical innovation and the lasting legacy of Brahmagupta's intellectual contributions. Brahmagupta's profound contributions to mathematics provided him with the tools necessary to address the challenges of his primary vocation, unraveling the mysteries of the cosmos through astronomy. Brahmagupta's profound contributions to mathematics provided him with the tools necessary to address the challenges of his primary vocation, unraveling the mysteries of the cosmos through astronomy. His mathematical insights were not abstract exercises existing independently of practical application. They were, instead, integral components of a broader scientific project, inextricably linked to his efforts to model and understand the movements of celestial objects. Astronomy in 7th century India presented a complex landscape of competing models and traditions, each vying for acceptance and predictive accuracy.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.